Hi dear students, this is Bhausab Sonani, Assistant Professor Department of Chemistry, Arts, Commerce and Science College of Art, District Palghar. Dear friends, if you are remember about the previous lectures, then in the previous part of the video, we particularly discuss about the vibration rotation spectra of the rigid atomic molecule, and then this vibrational rotational spectra of rigid atomic molecule is also called as the study of vibrating rotor. And after that we discussed particularly about the anharmonic oscillator, and in the discussion of anharmonic oscillator we also studied about the first harmonic, second harmonic and the third harmonic. Dear friends, based upon the vibration spectra, here we are going to talk about the study of structure of water molecule and the structure of carbon dioxide molecule. If you are remember about the number of vibrational degree of freedom that can be calculated for linear and non-linear molecule, and here with the help of this example of the water, this water is the non-linear molecule and it is having three atoms in its structure, so definitely it is non-linear triatomic molecule with a bent structure. As it is the non-linear molecule, so number of modes of vibration is given by the 3n minus 6, where n is the number of atoms. Therefore the total degree of vibrational freedom in H2 molecule is, that is 3 into 3 is 9 minus 6 will be 3. So which are these three vibrational degree of freedom, or the vibrational modes of vibrational modes, and definitely we will discuss these three modes of vibrational motion. So here this indicates the water molecule shows three modes of vibration, and out of these three modes the two are stretching vibrations and one is bending vibrations. So which are these three? Out of two stretching vibration, the first one is called as the symmetrical stretching and the second one is called as asymmetrical stretching, while the bending vibration is shown by this here. So these are the two important, and if during this vibration if there is a change in dipole moment, definitely that mode of vibration will be IR active and it will show spectra in the IR region. So here out of these three modes of vibration, definitely here we are able to discuss the spectra of this, and definitely here it is found that the symmetrical stretching or symmetrical stretching as well as bending mode of vibrations shows change in dipole moment during the vibration, and that's why in the structure of H2 molecule all these three modes of vibrations are IR active. This is the important. So all these three vibrations involve the change in dipole moment and hence these are IR active. So all the modes of vibration in the H2 molecule are IR active. So this is the important thing. If we will talk about the CO2 molecule, the difference between the water and the CO2 molecule is that here H2 is non-linear molecule but carbon dioxide is the linear molecule, because all three atoms are present in one plane, one line. So this carbon dioxide is a linear, but again it is triatomic molecule, therefore its a total degree of vibration motion is given by 3n minus 5, so that will become 4. Out of this 4 mode of vibration, which are IR active, which are IR inactive, this is the important part to discuss here. So this indicates, it shows the 4 mode of vibration. So out of this 4 mode of vibration, one is symmetrical stretching, another is asymmetrical stretching, and the two are bending vibrations. See, this is very important, but these two bending vibrations have the same frequency and therefore these are called like the these are said to be energy degenerate mode of vibration. So this is the one case, that is symmetric stretching, this is asymmetric stretching, and this is the bending vibration, but these two bending vibrations have the same energy, so these are called as energy degenerate. So actually in practice it has only the three mode of vibration. One is the symmetrical stretching, another one is asymmetric stretching, and the second one is called the bending vibration. The symmetric stretching mode involves no change in dipole moment, because This change is cancelled by this change. That's why the symmetrical stretching mode of vibration do not involve any change in dipole moment during vibration. So this is IR inactive mode of vibration and shows no absorption of energy. The asymmetric mode of vibration involves the variation in the length of the bond and hence there is a change in dipole moment during asymmetrical stretching. Therefore, it is IR active. It's very important difference to discuss here. While the bending mode of vibration also involves the change in dipole moment due to the change in bond angle, and that shows the absorption of energy in the IR region. So the value of mu1 bar and mu2 bar is greater than the mu3 bar because bending requires less energy than the stretching. So that's why in the structure of CO2 molecule, the two mode of vibrations are IR active and the one is IR inactive. Out of these three, the asymmetric stretching and the bending vibrations are IR active, while symmetrical stretching is IR inactive. So this is the infrared spectrum, and these are definitely the different. So this is the actually fingerprint region and group frequency in which we are getting the information about the different functional group. This is the important use of this IR spectrum, the IR region. That's why it is called as fingerprint region. The spectral region in between 1400 per centimeter to 900 per centimeter is rich in number of absorption bands, and these absorption bands and their intensities are typical for molecular structure. Under the study, slight change in the structure produces a change in the pattern of absorption. Thus, this part of the spectrum is characteristic of a compound and is called as fingerprint region. So next is the Raman Spectrometer. This is also one of the important. The rotational spectroscopy or the IR spectroscopy deals with the absorption of radiation, but the Raman spectroscopy involves the scattering of radiation. This is the main difference. Other spectroscopies involving the absorption of radiation, but the Raman spectroscopy involves the scattering of radiation. In the year of 1928, Professor C.V. Raman discovered that when light of different frequencies pass through gas, liquid or the solid, then the scattered light is absorbed at right angles to the incident light. This is very important, and for this discovery, this C.V. Raman got awarded Nobel Prize in the year of 1930 in physics for this discovery. Raman found that if mu I bar is the frequency of incident radiation and mu s bar is the frequency of scattered radiation, then the difference between the frequency of incident and the scattered radiation is the characteristic of the substance producing the scattering, and it is independent of the frequency of the incident radiation. This difference is called as the Raman frequency. So difference between the frequency of incident and the scattered radiation is called as the Raman frequency, or it is simply called as the Raman shift indicated by delta mu bar. Dear friends, if this delta mu bar means the Raman shift is negative, means the frequency of scattered radiation is greater than the frequency of incident radiation, then the Raman spectrum is said to consist of anti-Stokes line. So remember that for the anti-Stokes line, Raman shift is always negative, and if delta mu bar means the Raman shift is positive, it means that the frequency of scattered radiation is less than the frequency of incident radiation, then the spectrum consists of the lines called as Stokes line. So remember, if the Raman shift is positive, then it gives the Stokes lines, and if the Raman shift is negative, it gives the anti-Stokes line. The Raman shift generally lies between the range of 100 to 4000 per centimeter, and which means that the changes in the energy of scattered radiation in Raman effect corresponds to the change accompanying rotation and the vibrational transition in the molecule. This is very important regarding with this Raman spectroscopy. So this is the reason, this is the line that indicates the realized scattering. For the realized scattering, delta mu bar is equal to 0. Means the frequency of scattered radiation and incident radiation becomes equal. If delta mu bar is negative, then it consists of anti-Stokes line, and if delta mu bar is positive, it consists of Stokes line. So this is very simple. So definitely it is not too much important for you. But here, this is the This is also not important. Comparison between IR and the Raman, that is not too much important. This rule of mutual exclusion is very important for you all to discuss the different mode of vibrations in certain molecule. This is the important general rule about the IR and the Raman absorption established, and the application of this rule may be exemplified for the carbon dioxide molecule. According to this rule of mutual exclusion, if a molecule has center of symmetry, it's very important. If the molecule has center of symmetry, then the Raman active vibrations are IR inactive, and IR active vibrations are Raman inactive, means vice versa. And if the molecule has no center of symmetry, then some but not necessarily all vibrations may be both IR and Raman active. It's very important that whether the molecule has center of symmetry or not. In case the molecule has center of symmetry, then the Raman active vibrations are IR inactive, and vice versa. And if the molecule is not having the center of symmetry, then definitely that is some but not necessarily all IR as well as Raman active. So here we will talk about one example in which the center of symmetry is present, and the example is the carbon dioxide molecule which has the center of symmetry. So here the converse of this rule of mutual exclusion is also true. So here the molecule which has the center of symmetry is given by the CO2 molecule. So we'll talk about the CO2 molecule. CO2 molecule is a triatomic linear molecule, and therefore it has 3n minus 5 number of degree of vibrational freedom, that is number equal to 4. And this 4 rule of mutual exclusion can be understood with the help of this example, because it has the center of symmetry. As already we discussed about the different mode of vibration in the CO2 molecule, the one is symmetrical stretching, second one is asymmetrical stretching, and the third one is called like the bending vibration. So these are the 4. Actually it has the 4, but 2 bending vibrations have the same energy, so these are the degenerate mode of vibrations. So this is, again, you know that in the symmetrical stretching there is no change in the dipole moment during vibration. That's why it is IR inactive. I hope you are remember. But as this molecule is having center of symmetry, that's why IR inactive vibrations are Raman active. This is very important. Again, symmetrical stretching shows the change in dipole moment. That's why during vibration, that's why it is IR active. But as it has a center of symmetry, so it will follow the rule of mutual exclusion. So IR active vibrations are Raman inactive. Similarly, bending vibration in the CO2 molecule shows absorption of IR radiation. So these are IR active, and then these vibrations are Raman inactive. So this is the rule of mutual exclusion that can be studied with the help of CO2 molecule. So this is very simple. Here there is one example based upon the same. A substance was exposed to radiation of wavelength 4.5 into 10 to minus 6. The first Stokes line appeared at 4.5 into 10 to minus 6. Calculate the Raman set. What actually, this is the radiation exposure. So this is the incident radiation, and lines appeared. This is scattered radiation. But these are what? These are the wavelength. And whenever you will write the frequency in terms of mu bar wave number, then we will take the reciprocal of this. So with the help of this reciprocal, the reciprocal of 4.5 to 10 to minus 6, that is, this is 2.222 into 10 to 5, while the mu s bar means the 5.4 into 10 to minus 6 will be 1.825 into 10 to 5 per meter. And the difference between that is nothing but simply mu s bar minus mu I bar. There is a mistake here. It should be mu I bar. Mu s bar minus mu I bar. This is the difference between the frequency of scatter and the incident radiation, and this value is equal to 0.37 10 to 5. And this is the value of delta mu, means the Raman set. So definitely it's very important to discuss about such type of numerical based upon the molecular spectroscopy. So dear friends, in this way we try to discuss all the types of spectroscopy given in the molecular spectroscopy, like rotational spectroscopy, also called as the micro spectroscopy. Next one is the vibration, which is also called as the IR spectroscopy. And after that we discussed about the vibrating rotor with the help of vibration rotation spectra. And then we discussed that there are some molecules which do not obey the selection conditions for the vibration rotation spectra, and these are called as unharmonic oscillator. And in the last we discussed about the Raman spectroscopy, and then we have studied about the rule of exclusion. So in this way we tried to complete this molecular spectroscopy at our level. So it's very important. Definitely it has so many important concepts in this topic. I hope we will prepare for the same in detail, and you will go through the questions or the MCQ given in this topic also. Thank you very much.